In this video, we're going to look at basically a full revision of Year 11 methods probability. So we're going to look at summarising and displaying possible outcomes for chance situations using different sorts of sample space layouts and calculating probabilities of events. We're going to look at the fundamental idea of probability as being a numerical value for measuring chance, both a theoretical value and an experimental value. We're going to look at how you determine that numerical value. We're going to look at the idea of what we call complementary events. We're also going to look at the probability of combined events and how we display these combined events using Venn diagrams, tree diagrams, and probability tables. We'll look at the idea of the union of particular events, the intersection, as well as touch very briefly on conditional probability. We'll look at what mutually exclusive events are and how they are similar and different from independent events. So that's lots of things to get through. So let's make a start by looking at some of the key terms. So probability has a lot of terminology that goes with it, and so some of our key terms are words like trial, which is a single chance experiment, like one roll of a dice. So when we talk about a particular trial of an experiment, it means one go at it. An outcome is the possible result from the experiment. So the outcome is the result of the experiment. So if you roll a six-sided die, the possible outcomes you'll get are the number 1, 2, 3, 4, 5, or 6. Should have a 6 on there. And that list of outcomes that we have there is what we call the sample space, and it has this symbol here. This is the one that's most commonly used in the textbooks now. And the sample space is a list of all possible outcomes. So we might have it as just a list like I had up here, or we might write it as a set. And if we're going to use the set, we're going to use these curly brackets. Okay, and you need to get these curly brackets drawn right. So one of the ways that I teach my own students to draw these curly brackets is if you look at that curly bracket there, it is a forehead, it's a nose, and it's a little chin. So there's a little smiley face there, there's an eye there. So as you draw it, you say forehead, nose, chin. Forehead, nose, chin. And it'll help you to get the shape correct. The other word that we often use is an event. An event is what we refer to as a subset of the sample space. So one of these particular outcomes. And these different outcomes here we call elements of the sample set. So using a little bit of our set notation and our set language as well. So if we have an event as a subset of the sample space, it might be getting an even number when you roll a dice, it might be getting an odd number, but we define an event using a capital letter. So we'll say let, and that's a capital X, equal rolling an even number on a six-sided die. Often that's simplified right down to something that just says X equals even number. Simple as that, if the experiment is defined. Some of the other words we need to learn to use and make sure we understand exactly what they mean are probability and an expected number. So the probability is in fact a numerical measure of the chance of an event happening. And it's a number between 0 and 1. So your probability has to be either a decimal or a fraction. It can't be a percentage. Okay, so probability will be decimals or fractions, but chance is a probability, is a percentage. A probability. Chance is a percentage. So if in the exam they ask you for a probability, you better give your answer as a decimal or a fraction. Do not give it as a percentage. The other thing you need to know about probability is that in a chance experiment, no matter all the different possibilities of the particular experiment, all of the probabilities of those particular outcomes all have to add to give you 1. And on a scale of 0 to 1, which is where our probabilities fit between, the closer it is to the number 1, the more likely it is to happen. The expected number is the other thing that sometimes you're asked to work out. So based on the likelihood of an outcome, so based on the probability, how many of those outcomes would we expect in a given number of trials? So to calculate that, to calculate the expected number, we take the probability of an event happening and we multiply it by the number of trials. Now the expected number is just the number that we expect to happen. It's not a prediction of what will actually happen, but it is an indication of, given the likelihood of something happening, how many we would expect. That's why it's called an expected value, not a predicted amount. So to calculate the numerical value for probability, we have 2 ways of doing it. One is if we have some experimental data, and when we calculate the probability worked out from an experiment where we've done a repeated number of trials over and over, we get experimental probability. So the experimental probability is the probability of an event worked out from the repeated trials of the same experiment. And what we do is we put the probability of A, where this A is our event, is the number of times that A was the result in this experiment that had multiple trials, divided by the total number of trials that were carried out. The other sort of probability we have is theoretical probability, and that's the probability of an event based upon what we expect to happen. That's why it's called theoretical. It's what we expect to happen. So it's not a prediction of what will actually happen, but it gives us an idea of what to expect in the long run, which means that after many trials, this is approximately how many the proportion that we would expect to get this particular outcome. So for example, if you flip a coin 100 times, you would expect to have roughly half come out as heads, half come out as tails, but you will very unlikely to get exactly 50 heads and 50 tails. It's what we expect to happen. If you want to get closer to the theoretical probability, close to the expected value that for an experiment, you need to do lots of experiments. So anyway, theoretical probability. So the probability of event A happening is the number of favourable outcomes that contain A divided by the total number of possible outcomes. And we use this particular formula here. The probability of A is equal to the number of ways in which A can occur divided by the number of total things in the sample space. And finally, we're going to look at comparing events. So we're going to look first of all at what we call complementary events. Complementary events are events where there's only 2 possible outcomes, A and A naught. We say this is A naught or A prime. A and A prime are complements. And what that means is that with only 2 possible outcomes, the probability that it's A and the probability that it's A naught or A prime should be equal to 1. If we take this equation here, we can rearrange it to get the probability of A is equal to 1 minus the probability of A naught, or the probability of A naught is 1 minus the probability of A. So if the 2 possible outcomes are odd numbers and even numbers, and the probability of odd is 0.5 and the probability of even must also be 0.5. So the other sorts of events that we have that we need to know about are mutually exclusive events, and they're called mutually exclusive because they're a situation where you've generally got 2 events, well, you do have 2 events, where if one event occurs it excludes the other one. It excludes the possibility that the other one will occur and vice versa. So for example, a number being an odd number means that there is no way that number can be even. So a number being odd and a number being even are mutually exclusive events. So complementary events are mutually exclusive events. So we can go back up here and write that complementary events are also mutually exclusive events. But not all mutually exclusive events are complementary events. Let me show you. Say, for example, we had a car, and a car can be either a Ford or a Toyota, just to name a couple. But the fact that it's a Ford, the Ford, means that it is not a Toyota. It also means it's not a Kia. It also means that it's not some other brand of car either. And so being mutually exclusive does not mean that they are complementary events, because our definition of complementary events is that there are only two possible outcomes. And if it's not one, then it must be the other. So we have, let me say that again, our complementary events are all mutually exclusive, but our mutually exclusive events are not necessarily complementary. And then finally, we have independent events, where one event remains completely unaffected by the occurrence of another event. For example, if you were rolling a dice and you rolled the die, it would have no impact. The outcome of that roll of the dice will have no impact on flipping a coin. And so with independent events, normally we show independent events using a tree diagram, and we use multiplication, probability of A happening and then B, if they are independent events, is equal to the probability of A multiplied by the probability of B. But we could also roll the dice and flip the coin at the same time, and neither of them would have an impact on the other one in terms of what was coming out. And so we can change our definition to just probability A and B is equal to probability of A times probability of B. So what we're looking for with questions in the exams is they will use a combination of these different sorts of formulas and some of the other ones that we'll come across in the next video to ask you to solve probability questions, and they have them very, very often, very regular. So that brings us to the end of our definitions for probability. In the next video, I'm going to talk about displaying probabilities and how to go about calculating probabilities from there.